Okay, students, so we're back in lesson 4.8. I'm going to walk you through number 37, which is a navigation problem, and then we're going to look at some simple harmonic problems, motion problems, and walk you through how to do a few of those. So you guys should all be ready to go then to do your 4.8 part 2 homework assignment. Here we go. Number 37 is on page 336 in your book. All right. A ship is 45 miles east and 30 miles south of its port. All right, I'm going to draw a picture of that scenario first. So remember, we have the compass headings, north, south, east, and west. And if he traveled east and south, he's going to be over here in the second or in the fourth quadrant. So let's say he is here somewhere. Remember, with bearings, you always draw your triangle to the y-axis. All right, this is going to be our angle theta right here. And this would be 45 and 30 would be your vertical. All right, so this is where he's at. This is the port right here. And he's arrived down here. The pilot wants to, or the captain wants to sail back to port. At what bearing should he travel? So what I'm going to do now is just draw in a new coordinate plane. And basically I am now interested in this angle right here, which is actually going to be the same theta as what we were dealing with before. So this theta and this theta are the same. They're alternate interior angles. So if I want to find theta, I'm going to do tangent of theta is 45 over 30. And then theta will be the inverse tangent of 45 over 30. And then if you put that into your calculator and make sure you're in degree mode, you're going to get about 56.31 degrees. Now we have to put that back in as bearings. So with bearings, he wants to travel in the opposite directions of the way he came. So he's going to be traveling north and west. So we would say north 56.31 degrees west. And there's his bearings. All right, from here we're going to work on simple harmonic motion. So if you guys go to page 331 in your textbook, you can see some great illustrations and things like that, some formulas that you're going to need and so forth. So on page 331, you're going to see harmonic motion, and the model that they give is one that deals with bouncing a ball on a spring. And they talk to you there about what equilibrium looks like, displacement, and things like that. The period is the time it takes to complete one cycle, just like for a trig curve. Amplitude is your maximum displacement from equilibrium, and the frequency is the number of cycles per second. Now with simple harmonic motion, you have two formulas that could describe the situation. You're either going to have displacement equals A sine omega t or A cosine omega t. All right. A is your amplitude, again, just like it was for our trig graphing in lesson 4.6. So D is displacement. Or the distance that it moves from the origin. Okay. We'll just call that distance. And I said origin, that's the same as equilibrium. So okay, omega is your period. Actually, let's see. Let me go back. Omega has to do with your period. Here we go, period is 2 pi divided by omega, just like it was for our period in lesson 4.6. And t is time. Frequency is going to be omega divided by 2 pi. Okay, so it's the reciprocal of the period. All right, now I'm going to walk you through number 47, and that one is on page 336 as well. Okay. So on number 47, we know that the displacement is 3 inches. We know the amplitude is 3 inches. And we know the period is 1.5 seconds. All right, we're going to find a model for simple harmonic motion. Okay, the first thing you're going to have to do is you're going to have to decide which of the two equations you're going to use. Are you going to use this one? Or are we going to use this one? Which one's going to make sense? So let's plug in what we know into each. We know displacement is 3 and amplitude's 3. And first we're going to check this out for time equals 0. So we're going to put 0 in for time. We'll do that on both equations. Now, which one is a true equation? Does 3 equal 3 times the sine of 0? Or does 3 equal 3 times the cosine of 0? Well, the sine of 0 is 0. Is that true? No. We don't want this equation. The cosine of 0 is 1, so that's going to work for us. 3 equals 3. So this is the model that we need. All right, to write your model, you're going to always substitute in something for A, the amplitude, and something for omega. So we need to replace both of those. We know that from up here, we know the period is 2 pi times, or 2 pi over omega. Okay, so that's going to help us get omega. All right, we know the period is 1.5 seconds. So if we solve this proportion, we're going to figure out omega. Multiply both sides by omega. Take 2 pi divided by 1.5. And omega is going to end up being 4 pi over 3. Okay, so now it's time to use that to write our equation. So we're going to write our equation as d equals 3 cosine of 4 pi over 3 times t. And there's your model. All right, we're also going to look at number 53. Number 53 says, here's my model. All right. Part A, find the maximum displacement. Maximum displacement is the same as your amplitude. So that's going to be 1/4. Part B. Part B is find the frequency. Okay, up here we said frequency is omega over 2 pi. So that's going to be 6 pi over 2 pi, and that's going to be 3. Part C. Find the value of d when t equals 5. All right. This isn't going to be too bad. Now you might be saying to yourself, the sine of 30 pi, how do I find that? you remember when we did coterminal angles and we kept adding or subtracting 2 pi to angles to get them back to 1 revolution on a circle? Well, I can subtract 2 pi 15 times and end up with the sine of 0 pi. So that's basically 1/4 times the sine of 0. And we know that's going to be 0. All right, so at 5 seconds, our displacement's 0. In other words, the object's back at equilibrium. Part D. Find the least positive value for t for which d equals 0. Okay, so find t when d equals 0. So I'm going to take my equation from up above and I'm going to set it equal to 0. All right, so I'm going to multiply both sides by 4. Okay. And that's going to give me 4 equals sine of 6 pi t. Now I'm just going to ask the general question, when does sine equal 0? Sine equals 0, bear with me here, when theta equals 0, pi, 2 pi, 3 pi, etc. So that's what I'm thinking. All right, so that means 6 pi t is going to equal 0, or 6 pi t is going to equal pi, etc. So these values correspond here. Okay, if I divide both sides by 6 pi, I'm going to have t equals 0 and t equals 1/6. What's the least positive value for time? Well, that's going to be time equals 1/6. And that's the end. So if you've taken good notes over these problems and you've read page 331, you should be in good shape to answer those simple harmonic problems that I have assigned in lesson 4.8 part 2. Please let me know if you have any questions. Shoot me an email. See you guys later.